All right, so this is going to be the last part of section 4.6. So what we're going to look at here, we got two examples from the book we're going to do to finish stuff off. We got example 5, where they want us to go through and sketch f of x equals x e to the x. And since we have an e to the x involved, and e to the x has a horizontal asymptote at x equals 0, what we're going to have to do with this function here is we're going to get the plus or minus table, but then we're going to go back and check the limit at infinity and negative infinity, and that's going to tell us how we leave the graph. The previous parts we were dealing with polynomials or trig functions, so we didn't mess with this last statement here too much, but in this one we're going to have to be a little bit careful about the way the asymptote works. So let's see here. Start out finding the first derivative, which we're going to have to use a product rule. So I'll say x is left alone. Take the derivative of e to the x, which is itself. Plus, now I take the derivative of x, which is 1, and we leave the e to the x alone. I can factor out an e to the x and get this. So we'll get our second derivative, which we're going to base it off the derivative of this. So we'll leave the x plus 1 alone. We'll take the derivative of e to the x, which is itself. And then we'll take the derivative of x plus 1, which is 1 times e to the x. If we factor in e to the x out, we're left with x plus 1 plus 1. So we're left with x plus 2 times e to the x. So when we check for these critical points, there's no undefineds here. E to the x itself is never 0. X plus 1 is 0. X equals negative 1, so that's one of our numbers. And by the same reasoning, we get x equals negative 2 over here. So our chart, we really just got to focus on what's going on with negative 2 and negative 1. So we'll have negative infinity up to negative 2, negative 2 up to negative 1, and negative 1 up to infinity. So we're going to look at f prime and f double prime. At negative 2, f double prime was 0, and at negative 1, f prime was 0. So let's try to figure out what's going on with f prime. Let's take an easy to work with number smaller than negative 1, so we'll say negative 2. Negative 2 plus 1 is negative. And then e to the negative 2 is positive. So we're negative for all the region to the left of that 0. Let's look at a number like 0 to be to the right of this 0. So we're at negative 1 here. Let's look at 0 from there. So for x equals 0, we get 0 plus 1 is positive, and e to the 0 is positive, so we're positive out there. For f double prime, let's take a number from this region like x equals negative 3. Negative 3 plus 2 is negative. E to the negative 3 is positive, so we're negative there. Then we'll take a number to the right of negative 2, so we could use, let's use 0 again. 0 plus 2 is positive. E to the 0 is positive. So we're positive all the way out there. Okay, so now we need to check what's going on with the original function, x e to the x. So we need to see what's going on limit as x approaches infinity of x e to the x, and limit as x approaches negative infinity of x e to the x. Limit as x goes to infinity of x is infinite, and limit as x goes to infinity of e to the x is also infinite. So the top limit goes to infinity, so we don't get a horizontal asymptote there. Whenever we get the limit as x goes to negative infinity of x, that is negative infinity. And the limit as x goes to infinity of e to the x is 0. So you head off to negative infinity on e to the x. So this is an indeterminate form. So we're going to need to do that algebraic trick of shoving x downstairs to set it up to use L'Hopital's rule to figure out what's going on here. E to the negative x as you go to negative infinity is 0. And x to the negative 1 as x goes to negative infinity is also 0. So we're in form 0 over 0, so we can use L'Hopital's rule for this one. And e to the x is its own derivative. And x to the negative 1 is going to give us, let's see, what is that going to give us? That's going to give us negative x to the negative 2. I'm wondering if this is going to go in. I feel like this is just going to keep turning out into indeterminate form again and again and again. Let's see. So limit as x goes to negative infinity, b to the x is 0. And negative x to the negative 2. That's, graph of that looks like this. So that goes to 0 as well. So we're still in the form 0 over 0. Okay, so let me look at the book real quick here and see what I've mixed up. Okay, so it looks like to get the limit to go out, instead of pushing the x downstairs like I did, because this'll, if we go this way, this will keep giving us we'll keep getting form 0 over 0, so we kind of get stuck. So what I needed to do is pushing the x downstairs with x to the negative 1. That was the wrong way to work on this. What we needed to do is push e to the x downstairs as x over e to the negative x. So yeah, this way you would get positive x to the negative, or positive 2x to the negative 3, which limit still goes to 0. So you just kind of end up in 0, 0, 0 form the whole way down if you have the e to the x in the top. So if we set it up this way, let's see here. Limit as x goes to negative infinity of x is negative infinity. Limit as x goes to negative infinity of e to the negative x. That's minus negative is positive, so this is e going to infinity. So we get an infinity over infinity form. So we're okay to use L'Hopital's rule. When we do that, we get limit x goes to negative infinity of 1 over negative e to the negative x. And then if we let, if we try to evaluate the limit at negative infinity, this becomes e to the positive infinity with the negative sign out front. So you get 1 over larger and larger and larger negative numbers, and that tends to 0. So we get a horizontal asymptote at x at y equals 0 as x goes to negative infinity. So we should have everything to graph this now. I'm going to throw away the scratch work I did that went the wrong direction, where I pushed x downstairs instead of trying e to the x downstairs. And we'll start building our chart up. So we got the points. We need to figure out what's going on with the point negative 2 and negative 1. So I need to know what their actual y values are. Negative 2 is going to be a point of inflection. So it's going to be at x equals negative 2. Now I'll figure out the y value. And then since we go from negatives to positive across this, that's going to create a relative minimum at x equals negative 1. So we'll need to find the corresponding y value. So for this, I'm going to go to the calculator real quick here. We're going to say, what's x e to the x? So x times e to the x. And we want to know what happens when I put negative 2 in. I get back negative 0.271. And then what happens if I put negative 1 in? I get back negative 0.368, I guess we could say. All right, so at negative 2, we get negative 2.71. At negative 3, we get negative 0.368. We know as we head off towards negative infinity, we approach 0. So we know that this is going to approach 0. I should check the shape I'm supposed to make. Decreasing and concave down. So luckily I'm making the correct shape through there. It's as you move from left to right, the y's get smaller and it's opening downwards. Between 2 and negative 1, we're decreasing, but we're concave up, which means this shape changes to looking kind of like that. Let's see. Something like that, where it's opening upwards. And then as we get beyond that, we go concave up and increasing. And our limit as we go to infinity is infinite, so we just kind of peel off and head upwards while we open up. Okay, so that gets that one done. The final one that we're going to take a look at is this example 6 from the section. So I know y'all should have talked about how to do this in like pre-cal, or for this particular type here, if you were asked to graph this rational function, that should be something you talked about in Algebra 2 and in pre-cal. So it's 3x plus 2 over 2x minus 4. Again, for the AP test, they want you to solve problems using calculus. So if you did this the Algebra 2 method to get this, where you never took a derivative or never talked about concavity or increasing or decreasing, chances are you're not making too many points on it. So let's take the first derivative. I'm going to have to use the quotient rule, so that'd be bottom left alone, derivative of top, minus top left alone, derivative of bottom, all that over the bottom squared. This simplifies to, actually we're going to have to simplify it and need more room. So it's 6x minus 12 minus 6x minus 4. That's all over 2x minus 4 squared. These will cancel. So our first derivative is negative 16 over 2x minus 4 whole thing squared. Okay, we'll leave that way. And then we're going to take the second derivative, which is, we're going to use a quotient rule again, so it's bottom left alone times the derivative of top minus top left alone times the derivative of the denominator. So chain rule applies, 2 comes down, leave the inner part alone, multiply by the derivative of the inner part, and that's all over the denominator squared. So it was squared, so now it's to the 4th. Okay, 0 times anything is 0, so this term is going to go away. Minus a negative is positive. 16 times 4 is 64, so we get 64 times 2x minus 4, all that over 2x minus 4 to the 4th. One of those 2x minus 4s can cancel, and you'll be left with 64 over 2x minus 4 cubed. Okay, so both of these are 0, or sorry, both these are undefined at x equals 2. So when we go to build our table, we have x equals 2. Our first derivative and our second derivative are both undefined there. So we're going to take a number to the left of 2 and see what it does to the first derivative, and then a number to the right of 2. And then we'll take a number to the left of 2 and the right of 2 of the second derivative and see what happens there. And then after that, we'll need to look at the limit. Since it's a rational function, we'll need to see what the limits approach. And That'll tell us what our horizontal asymptote's doing. So I'm going to take, let's see, for f prime, let's use 0. So if I put 0 in for f prime, I get negative 16 over negative 4 squared, which is positive 16. Negative 16 over positive 16 is negative. If I put 3 in, let's see here, I get negative 16 over 3. That'd be 6 minus 4 is 2. 2 squared is positive. So I would get negative again. So we get that. For f double prime, I'll put 0 in. I'll get positive 64 over negative 4 cubed. Negative 4 cubed is negative. So it's positive over negative, so we're negative. And when I put 3 in, see, 2 times 3 is 6. 6 minus 4 is 2. 2 cubed is positive. 64 is positive, so we're positive over here. Now I need to see what's the limit as x approaches infinity or negative infinity. So I'll do limit x approaches infinity of 3x plus 2 over 2x minus 4. And we'll do limit x approaches negative infinity. Okay, so as we go to infinity, this goes to infinity, that goes to infinity, so we're in form of infinity over infinity. Down here, this will go to negative infinity, that'll go to negative infinity. So in both cases, we can use L'Hopital's rule. So I take the derivative of the top and the derivative of the bottom in both cases. Derivative of the top is 3, derivative of the bottom is 2. Down here, derivative of the top is 3, derivative of the bottom is 2. So both cases end up going to 3 halves. So as you go to x goes to infinity, you get 3 halves. As x goes to negative infinity, you get 3 halves. So let's see what we have. In the original function where you get division by 0 at 2, there's going to be a vertical asymptote there. So we have a vertical asymptote at 2. At 3 halves, we have a horizontal asymptote. So 3 halves is 1.5. I put a dotted line through there. And then we start out decreasing concave down, which would be a curve that's decreasing concave down will be a curve that looks like that. So it's getting smaller as you move from left to right, and it opens downwards. Then we got to finish that up with decreasing but concave up. So over here, our choices are this or this. This is decreasing concave up. This is increasing concave down, so we want the top choice. And that would be a pretty good representation of our graph. I guess you see where the y-intercept is. Y-intercept would be at -1/2. So I have kind of on my graph here. Sorry, I should say y-intercept's at -1/2. So this initial one, you're decreasing and concave down. And then you're decreasing but concave up. Okay, so that's a little bit better. Okay, so that's we're gonna stop there. That wraps up the sections. So that is section 4.